is Pedro Vilaça, that weird letter. So I am professor at Aalto University, where I live and work in Finland for about 10 years. I have a career of over 25 years of professorship, and my eyes don't see well, so I just put this wrong signal there, and I noticed my age is exactly taking over my capacity. But I hope with my age also to bring some experience and awareness on the perspective of what Aalto University is, and one of the objectives of today's lecture is also to understand and to promote this relation between Europe via Aalto University and Universidad de los Andes in Colombia. So we can progress. So the presentation will be divided in two blocks. The first one addressing what Aalto University, the School of Engineering, and in particular the Department of Mechanical Engineering are, how we are organized, and also in cooperation with the Universidad de los Andes and Colombia. So Aalto University is located in Finland, north of Europe, and it's in the city of Espoo, which is very, very close to Helsinki, in Helsinki zone. And our campus was designed by Alvar Aalto, magnificent and distinct world architect, and we took his name, and later on you will understand better why. So, from where we are to my home university, we have over 10,000 kilometers distance, but fortunately that we have open heads and willingness to make this distance very short and take advantage of our willingness to learn, also sharing different cultures, and this brings additional benefits beside the knowledge also. So we, in comparison, the population of Finland is 1/10 of the population of Colombia, also with much less, although with a smaller area of Finland, much less population density, and we already represent a very interesting amount of per capita capacity in our gross domestic product, and we are very proud of the cooperation with Colombia that is growing fast in Latin American domain and in the world. One of the most distinct growing countries in the world. So we have, in terms of countries, we have 100 years old difference. Okay, Finland is one of the most recent countries in Europe. It became independent from Russia in 1970, although it is an autonomous zone from Sweden to Finland first, and then from Russia from a long time ago. And we have this important, also historical scope to consider, which has benefits, enable us to have very modern, industrially active, and also from the education point of view. So Finland is typically ranked top in the world in terms of skills in science, mathematics, and reading, according to his ranking, and is for the 5th time in a row considered the world happiest country, whatever that can be, okay, if you can measure such a thing. It is related with quality of life, life expectancy, the conditions to access education and health, and very important, this equality, diversity, and inclusion also. members from all over the world. So Aalto University lays in a beautiful Otaniemi Bay, and Finland has distinct cities. Are the capital, Helsinki, that was the capital oriented for Russia, and originally our capital of the autonomous country domain that is still nowadays was Turku, oriented for Sweden. Other very important cities are Oulu and Tampere, okay? And a significant part of Finland lays above the Arctic Circle, okay? And in fact, we have in Lapland, Santa Claus, and so we have here, Papua New Guinea. Very important. Culture is very important. We feed our spirit culture. Distinct aspects. We have this Lapland, Laponia, but outstanding is that the country encompasses about 200,000 lakes, and we only consider the ones that are bigger than 500 square meters. We have beautiful landscapes, natural reserves like Yuxu, beach, long beach, sandy beach places, beautiful archipelago, the Tanya Gulf, and the Baltic Sea, and also magnificent parks all over the country. Very important in terms of support of the quality of life is the economical impacts on the world of industry, and the most important aspect that Finland reached since the Second World War was the installation of world-level competitive companies. And among these, we have the biggest one in stainless steel production, Outokumpu, and SSAB, a very important steel mill in production of special steels, most oriented for that, high-strength steels in sheet metal and plate. Meyer Turku is an outstanding shipyard producing large scale of ships and boats, and then we have dedicated also production of ships for traveling in domains of ice or very close to 0 degrees operation. Mining and the paper industry, Metso is one world leading company. Among our distinct companies in electronic and network, we have Nokia, that's very well from all over us, but still everywhere around that, because it's one of the 3 leading companies in radio network signals. So it's with us still, so we don't see hardware, but it's still produced by Nokia and some other companies. Not so many. ABB for automation, digitization, electronics. Kone for vertical transportation. You probably see the lifts, the automatic staircases. Kone cranes for crane systems. Wärtsilä is the biggest one, producing engines for ships. And Movente now also a major player in gear systems for windmills. And so we have, these are outstanding companies that in a country of 5 million people play a role of being among the best in the world. And this is the source of this happiness and quality of life. So, but this feeds also from the education. Aalto University is a very recent university in terms of installation in its name, but is based on the merging of significantly old universities, like the Technical University of Helsinki, the University of Arts from Helsinki, and the University of Economics. So, the name of Aalto is honoring Alvar Aalto, is pioneer of modern architecture and design, and he was professor at MIT. He was an entrepreneur and an artist, a technical artist from architecture also, but also from design. And so his name encompasses this technology, art, and business. And that's why in the distinct name we adopted very honorably for us the name of Alvar Aalto University. In terms of strategy, the research and innovation and the impact are the three pillars of any university in the world right now. Distinct in our approach is that the education and impact are supported by a deep investment in research, and we transfer actively, even in bachelor and master education, but also the doctoral education, the research actions, and we collaborate with companies in aspects of innovation and not so much in aspects of service. Okay? So we are committed to the impact, promoting innovation in the companies and setting new companies in the economical sector. In terms of numbers, and we have about 4,600 staff members, with about 400 professors, and 12,000 students, encompassing master and bachelor students, and we have 1,000 employed doctoral students. Okay, and we don't call them anymore doctoral students. This is what we call them doctoral researchers, because we are very proud of providing conditions for them to set their life on the base in terms of funding, conditions for implementing their innovations, and promoting them for further steps in their life. So our doctoral researchers are already active members of the society, so in respect of students. So we see some downturn coming from COVID and research impacts and the various sense that they existed in Greece in the last 2 years. I think this number is outstanding. There are not many universities that reach this number of the academic faculty staff. 47% is international, and I am one of those examples. Okay, so we are we look for the best, and we don't look for the easy or the local ones. And for that, we also need to be attractive for the students to look for us, and for the international best research and teaching staff to be willing to come with us. The impact this has is that our research impact is growing, and also we are replacing the internal research funding for companies and services into impacting research and international competitive funding. So we rely less and less in national funding, and we are more competitive, and this means that this was originally the start of our university, healthy, high contribution for the service part, and now we are placing research that is innovative, step forward from the state of the knowledge. In terms of sources of funding and expenses, we have the structure that you can see. I will go over this without much emphasis. It's available for discussion if needed. But I would emphasize also that this technology transfer and the installation of new companies is growing very, very significantly. That is number from 0.1 million euros to about 8 million euros in technology transfer. These are the patents that we are selling, starting selling at Alton, selling it, transferring gas into and commercializing them with the existing companies for the companies to make money. It's not our duty to make money out of them, except this signal that's coming from impact research. This is one of the most important things. Okay, our ranking is in the KIAS ranking we have 116. Shanghai ranking is among 300 and 400. We have tens of thousands of universities in the world. This is already very, very impressive. And among the young universities, we are the first in Finland, among the first in Nordic countries, the third in Europe, and the ninth in Europe. Not sure about this ranking for university level.
We are about 220, 250, 220, 220.
It's already very distinct. So our university operates in terms of research and education, organizing 6 schools. From the Technical University of Helsinki, we have now 4 schools: School of Science for IT, chemistry, and physics, through the various scientific aspects and market. Then the School of Electrical Engineering, the School of Chemical Technology, engineering, I think now, and then the School of Engineering that encompasses mechanical engineering, civil engineering, and built environment. And then the School of Business, from the previous business school of Helsinki, and the School of Arts, from the previous art school of Helsinki. Our School of Engineering is organized in this department, as I told, and we are very proud of having some distinct infrastructures like this Alto, ICE, and Wavestone, which is a leading infrastructure of excellence in the world research in ICE. And we are located in this very high 60 degrees latitude, okay, compared to about very near 6 or something 7 degrees of latitude Colombia, so quite high, and so the ice and Arctic, but also the exploration of the plastic. Such freezing conditions are very important for us. We have the mechatronics field with this platform of autonomous campus, the product design, the additive manufacturing, the digital design laboratory, and then very important infrastructure, which is the design factory. Okay? I think that Professor Gonzalo and also Sylvia, she's your team at this moment. They have been there. We are active promoting the expansion of our design factory also in the University of Los Angeles. They are in hundreds of universities around the world. So these are the members of our department, about 300 staff, 30 professors, okay, and a total funding of 17 million euros, about 1.2 euros, about $1.2, okay. And half of this is coming from basic funding, and half of this from competitive. We are responsible for the operation, for part of our salaries, and also for the maintenance of all infrastructure. So, at our mechanical department of mechanical engineering, the passion and research teach develop solutions targeting social needs and shaping a safe and efficient future generation of materials, manufacturing, structure, machines, ships, energy flows, and systems. The department in multidisciplinary research conversions on the Arctic technology, sustainable energy vectors, and digital technology. So these are our main strategic flags: Arctic technology, sustainable energy vectors, and digital technology. The focus of education are in mechanics and energy science and technology. Good part of the needs to industry generates a impact that can be seen in business and society. So notice that we have the research, education, and impact, but the order method. We are organizing 7 research groups. I operate as head of the group, as head of the department, but my research line is much more in department of materials. But we have 2 groups of energy, energy conversion, and energy efficiency and systems. We have the marine technology and solid mechanics encompassing the large research in ice mechanics, advanced manufacturing and materials, product development, and electronics. We are now striving to have an organization, but also more critical mass for addressing the research, innovation, and impact in these 4 groups, which is a strategic evolution from the previous operation, and with a transversal fundamental research, which we call in-depth. So this was the presentation regarding what we are. So it's important I think that's one of the most important roles that we can promote with this cooperation. And we can address the definite problems of rescue there. Or now, how do you see? Should I go on? Probably it's there. So, and I prepared now a more technical, technological presentation on an issue that is a little bit aside from common awareness. So most of the welding and processing are nowadays, since the start of the 20th century, for most based on fusion, which enables a quite flexible approach of application of energy and processing and enjoyment of materials. Solid state still provides, although the oldest group of solutions, it still provides the most advanced solutions for the aspects where fusion, welding, and processing are not addressed. So we will start with the technological and historical scope, fundamentals and geometry, and overview of techniques and applications, as well as some innovations that are coming from my research group in particular. This is going to be very descriptive, not formative, okay? More informative, okay? More National Geographic. At the end, you think you know something, you have just an idea that these things exist, and I hope they keep your willingness to go further and make the difference. As you will see, we have set up some openings based on this innovation. So mastering this knowledge really opening an opportunity for significant impact with benefit for everyone, for the whole society starting with now. So, solid state, side by side with fusion and brazing is one of the groups of material processing for the modification of relational conditions, metallurgical and joining of materials. So all the elements are processed under fusion temperature, different levels of energy, and we can use heat energy or mechanical energy or combination. Eventually, there may be some liquidifying layer in the processing zone, but if that layer is projected out, joining mechanism is relying on solid state concepts. So, forging is in the base of the evolution. Forging, in fact, forging and brazing were the only solutions for joining of materials since the Bronze Age, and encompassing lots of your elements that we can see in Museu del Ouro as an example. Outstanding constructions, very rudimentary approaches of forging and brazing. And there was a significant evolution at the start of the 20th century. In fact, it is the background of the technological and innovation that enabled Germany in the first place, but many other countries in Europe in a modern wave of taking over the evolution in terms of technology. But it came out as the First and Second World War, first mostly in Europe, second completely in the world, supported by the new construction that was only enabled by joining evolution. And so we have electric arc-based processes, family from very small thicknesses to high thicknesses. But anyway, the automatization and control, and now going further in more specialized applications and high probability of small sheet metal for the industry as a solution for some synergistic market, several variants of student transfer, and advantages with flux core arc welding also. In side by side, we have the combustion-based processing, mostly for thermal treatment and brazing. Welding with oxy-fuel gas welding is not anymore the best solutions, and we only address these two processes that are the best solutions in something. We invent lots of things, and we invent processes every day around the world. Only when they are distinctively better than the existing state of the art in some domain of application field, they become eventually possible to transfer into industry and society. But what is required from a mechanical engineer, an engineer in general, okay, is the capacity to select the best solution to process that geometry, that metallurgical aspect of the material, local series for some level of quality. So the success depends a lot on the knowledge and not on the process. No process is the best in this. Okay. A very distinctive, probably quality-wise, the best solution is actually in welding, operating from vacuum to atmospheric level of pressures, and also laser with some more limitations of the photonic interaction between the material surface and absorption. We have different active medias that adapt also to different domains of application. So these are used in joining, but also in cutting, in coating, and processing of surface. So this is the domain, also in thermal treatment, where this field of technology is applied. And so forging is in the origin of joining of materials. And why was forging the only possible solution, or brazing and fusion was not applied until the high power density was possible to implement with based on electric arc, electron beam, laser, and so on. So what was the problem? We had power sources, okay, and very nice automatization based on human. So we apply heat, but why? So we understand that in liquid, it is more or less intuitive that most of the materials can mix together, and then based on oriented solidification, which is called epitaxial solidification, they can be brought into the solid state functional condition. Why it was not possible to apply fusion here before the high power density power sources were available? Because these metallic components have properties that transmit the energy, so they are energy vectors also. And so if the power density is not able to promote increase of temperature higher than the rate of transmission, heat conductivity directly, but also heat capacity, mass, But if the flow of energy overcomes the rate of energy that is introduced in the material, when you have the process at home near the melting, everything is melting. So it was not possible to process materials in fusion. Okay, and so we could only use brazing where we have fuel and metal in fusion, but the basic are in solid state, and therefore the resistance, mechanical resistance is low, or solid state. And solid state will really provide high level of performance in the same level of the materials originally or even better. Anyway, it was not very flexible. It's not very easy to produce forging. Depends on these constraints. So what they were doing is just the amount of mechanical energy available was not enough to apply the conditions to activate the joining mechanism. And so they have to apply a heat source, bring down the resistance of the material with the increase of temperature, the yield strain measure power quantity of the material that comes down with the production of heat as temperature measures the vibration and increases between the particles. And when this distance increases, you can apply deformation, and with deformation, you bring the internal material to the outside, and you create this new chemical reactive state, where with mechanical activation, energetic activation, mechanical or heat, we can then process it. So this was mechanical energy, mostly activation. But this knowledge is the base of many of the things that you can see in the beautiful Museo del Oro. And you can see that the shape, complex shape, was brought together by forcing already to the more simple shape that was produced by cutting techniques. And so forging and all this knowledge really is close to us, but also provides nowadays the solutions addressing domains of joining materials that are sensitive to heat, sensitive or very different in physical properties, like welding an aluminium with a steel. Okay, steel has 1500 centigrades of fusion, and aluminium has 500. So when aluminium is at the melting temperature of steel, it is already vaporizing. Okay, and when we have the liquidification of aluminium, there is no liquidification of the steel. So this is an example where different materials can be brought together in solid state, and forging still provides significant amount of solutions for that field of where fusion welding is not able to address. So there is a domain of energy below which we cannot change the original materials. And why does solid state materials don't come together? Fortunately, that's why we can interact, we can sit, we can bring components together. Why they don't come together? Do you have any idea? Because that's so you have to overcome this stability, and that there is a threshold of energy above which we can start implementing the activate joining mechanisms, and below which we have no condition to overcome the stable operation. So materials are at the surface are different from the interior. Okay, at the interior you can understand that you have attraction and repulsion forces in between particles. When you cut and create a surface, any particle at that surface will be out of balance. It will be repelled or it will be attracted. And if nothing happens, all the matter would disappear or would collapse in an infinite mass. And another energetic solution is that they interact with the environment, energy, and the chemical conditions, and they are brought to a new stable equilibrium. This is the oxidation processes. These are the relations with oxygen and hydrogen and carbon around, and provide different distinct properties. And so those surfaces are stable. You need to bring material that is not stable to the surface, that are looking for a new physical equilibrium, okay, to activate the joining mechanisms in solid state. Okay. So you need to get rid of this stable, the original surface. And that's why it is threshold operation. So melting based fusion based processes are in this line where we have in this graphic, sorry, we have water temperature as a major effect of heat energy, although heat energy also produces expansion and residual stresses, impact, and mechanical energy produces information, general pressure, but also generates dissipation by heat. But if we plot this pressure versus temperature as most important consequences that results from the application of heat energy and mechanical energy, we see that above the melting temperature with no mechanical energy, you have the most of the fusion welding processes. And then you have a very important process that is based on fusion, but is insulated from the remaining world with the forging zone. And that is the most automatized welding process probably. Which one is it? The name is there. So resistance welding. Where do you find it? A lot. Anyone? Every time you have a news from automotive industry, what do you see around? Don't you see some robots around, sheet metal, bringing some electrodes for spot welding? Okay, automatized or robotized, manual applied, not so typically. So resistance welding enables us to have melting, but because we generate plastic information from encompassing the melted zone, we can repeat it at high pace, and the insulation with the external environment provides great quality in relation to and repeatability in relation to the process with non-mechanical energy. And then bringing the process into the domain of solid state, we have processes that generate the heat source generates a liquidification interface, but with projectile liquid interface as a way to generate new chemically active surfaces. So there are two ways to generate these chemical active surfaces, new surfaces that are looking for a new energetic balance, and that if we bring the materials together, we can then activate these atomic bonding and diffusion that are going to happen. So we can make it by bulk plastic deformation or by liquidification and projecting out the liquid zone, leaving behind the chemically active surface. The processes are high frequency welding, which is everything that you have here, everything, okay? All this, okay, is it open? Okay. Which you cannot see inside, it's not open. But all this is produced by high frequency welding, okay? It's brought together because you can extrude aluminum, it is not extrude steel, because the matrix are made of steel, and then they're out with the extrusion process. So these are welded, and they are welded continuously for many hours. So this is high frequency welding. Flash welding is also important, mostly when we apply studs. Okay, so they are all around everything. Okay, all the tubular systems that you have, they are all around. We are seated, we are living on top of our cars or transportation systems, in bridges, okay, everything that's almost, you can imagine, our life depends on this knowledge and capacity. And so, new solutions for challenging conditions is the job of researchers, and this solid state encompasses lots of those key knowledge for innovation. When the materials are very ductile, mostly face center cubic structures, we can have processing in cold, low temperature without crystallization, because these locations require very low level of energy dissipation, And we have the cold welding concept. And examples of this, we will see that the long kilometers of wires in bobbins and so on, they are extruded in copper, aluminium, even steel, but they don't come with kilometers. So the wire systems have to be welded together. So both welding is quite applied in that field. And then we have this visco or third body domain, viscoplastic innovation. And this is where most of innovation is coming from now. You probably play with this when you again. You have, I don't know what is the name, plasticine? You make when you
Plastilina. Plastilina.
Plastilina. So this is the plastilina domain. Okay? Material behaves as a liquid, but retains the physical formulation of a solid and constitutive relation of a solid. So this is why we call this intermediate third body. The main joining mechanisms are based on atomic bonding. Any two particles, when they are apart, they have some gravitational effect of attraction, but when they are brought together, they start to create some repulsion because two masses cannot exist at the same time at the same position. Okay, so there is a distance in between any kind of two particles where the attraction and repulsion forces are in equilibrium. So for that, if resultant 0 flow, you have the lower energy of the system. It means that bringing those particles from that lower energy, you have to apply energy to come out of this lower energy value that you have. Okay, this is the cutting technique. We have it as joining and coming out. When it is joined, we have to apply energy, and that is the cutting. This is for low temperature operation, where the materials the distance between the particles is not enough to activate diffusion. We know diffusion from carbon in steel structures, where it's used in general, but diffusion of particles, of metallic particles, is also possible, also similar atomic radius. And just depend on the distance between the particles. So when you have higher temperature for manufacturing, you can activate diffusion, which is strong bonding. When you have low temperature, the distance is not enough to enable the mixture of particles, and so you have atomic bonding. Or you have those also in some domain of application. We have also mechanical interference, or we call clinching, that we take advantage also. And so the requirements are these, and if you understand these, everything that comes after is obvious for you, and you will be very rich in about 1 or 2 months from now, because you will be able to invent something when you wake up tomorrow, and probably set some patent and the company comes. Okay, so the world is willing for solutions of optimized structures that are not. So we do structures that are very far away from the optimal performance because we cannot combine different materials and different thicknesses in an easy way. So joining of materials, why do we need joining? That is also a question, okay? So what are the alternatives? We can produce in castings, okay? We can produce nowadays with lots of additive manufacturing techniques. The problem is that none of those technological solutions provide the performance of thermomechanical processed sheet metal or plates that are optimized in terms of strength and toughness, impact toughness, toughness in terms of energy capacity, information, materials. This is not possible to reach without accepting basic shape. And so we need joining techniques to bring these high performance materials into complex shapes. And so everything lies on the quality of the joint, because the base materials are already very high performance. And so the engineering knowledge in innovation for many solutions that we need to combine between now and for thermal properties, electrical properties, between lightweight and the high performance materials. stainless steels or steels and magnesium alloys, titanium alloys, all these world of metallic materials. But nowadays also we are having and addressing solutions for joining metals to polymers. Okay, wow, completely different worlds in terms of physics. So these are the fields where this knowledge that we are addressing of creating new chemically active surfaces, and once we have them, then with mechanical or heat power in some time, that's the energy aspect of mechanical energy, heat energy, promoting the activation of the joining lines. The atomic bonding, diffusion, and cleavage. So, new chemically active surface requires that we get rid of the original surfaces. We do it by liquidification or expelling out the heating of the interface and getting the new chemically active surface behind, or bringing the inside material to the outside by plastic deformation. Every time we have these locations at the surface, we expose new chemically active surface that is looking for a new balance. Or we can keep it the original surface. We break the original surface in very small, fine amounts that we then disseminate inside of the processes, so that the togetherness doesn't play well. So we have with more heat energy and low mechanical energy, more diffusion. We expand the material and we bring the diffusion mechanism. We have more atomic bonding for low heat energy and high mechanical energy. And then we have this domain where we can find diffusion and atomic bonding. So now we will overview some of the applications of these concepts in existing techniques. Some are more conventional, some are more advanced. So the first is this high frequency welding. This is written in Portuguese, so I'm not sure that you can understand it better or not. This is the process where liquidification of the surface is generated by Joule effect, because you know that high current promotes skin effect. So the high AC current that you flow to the material, the more close to the surface is the balance for energy to be able to invert the flow of energy field or electrical field. So in DC current, direct current, okay, you have the flow of energy flowing uniformly to the component. In AC, it starts to get closer to the surface. Okay, and as you increase the frequency of AC current, you increase the skin. And if the frequency is very high, so you know what is the frequency in our network typically? So 60. Yeah, 60. So you see that we are now speaking 100,000 to 800,000. So the skin effect is very high. You have liquidification of the surface. Materials are brought together. They are formed. They are brought together, and when they are projected after this is the generation of energy. Electrical field times conduction zone, contact zone. And this is how we produce them all these complex closed shapes, typically tubular shapes. In flash welding, we produce liquidification by high voltage, similar to electric arc, but without the plasma domain. So we don't have low voltage and high current. We have high voltage and low current. There is a liquidification. We bring the materials together. The original interface liquid comes out. You have new chemically active surfaces, temperature, okay, pressure, and at the same time we apply this mechanical energy, and you activate diffusion, mostly based on diffusion temperature. Because behind the liquidification, you have solid but very high temperature. So the diffusion is very high and the quality is extremely high also. A variant or a specific aspect of this is the welding of studs. Okay? In your car, all your interior part is plastic, and the body in white, okay, the chassis is all metallic. So how do you bring them together?
it's mostly because you weld studs in the metal and then you clamp the plastics to these studs. Okay, that's an example. But studs, thread studs, five studs, etc., they exist in many. It's the same as the flash weld. You have a very specific profile where you have something like this in the stud, the body of the stud, and this creates the distance in between the base material, and then you have the sparks with high voltage, okay, and low current. You have the spark system, the liquidification of the surface, okay, and then you destroy the mechanical gap providing the element of the stud. So the stud is not flat, there is a distance that is pre-described by, pre-established by this shape of the stud, and bringing them together, liquid goes out, and you have the high temperature under pressure generating and sometimes the activation of joining mechanisms and these new chemically activated surfaces. In the other extreme, where we have no heat power source, so some heat is generated in plastic deformation, but we can bring together materials that are ductile by plastic deformation. This is the offset flash process for welding wires and structures by specific plastic deformation, bringing chemically active surface that under their mechanical energy deactivate mostly atomic bonding. You have these Coca-Cola aluminum bottles, beer bottles, everything okay, welded with clinching and a bit of cold pressure. So you can only apply these in materials that are ductile because you don't have a heat source, and so relies mostly on the new chemically active surface relies on movement deformation. Diffusion is the name of a joining mechanism, but also of a process where you don't have full deformation. The surface stay essentially the same. So this is one of the most original additive manufacturing methods, where you bring different components, keeping the original shape into final components. And every time you apply two components with some inherent roughness, the pressure is not uniformly distributed, and there is high contact in the projected zones in between the components. With the high temperature, below the melting temperature, you are able to plastic deform the contacting zones, getting rid of the original stables, oxidized surfaces, and generating the low energy that will then spread as a lower energy solution for the metallic system. This is diffusion, and it is produced out of so ovens with mechanical system inside and controlled atmospheric environment. Ultrasonic welding. In elastic domain, you undergo an hysteresis cycle. So you do the elastic tension compression system. We lie to you every time. Okay, we simplify the plastic mechanics. It's one of the worst things that we can teach, but we still teach based a lot on the Newton laws and things like that. Nothing exists like that, fortunately, and we know it. And Einstein established this equivalence of the mass and energy and the relativity of the energy with the time. So, and classic mechanics is essentially alive, basic formalization of our mechanics knowledge, and elastic deformation also doesn't exist. Okay, so elastic deformation is based on the exploration of the metallic bonding between different particles, so you change the distance between them, but you always violate some of these most extreme distance between the components. So each electrode belongs to several nucleus, okay, of atoms of the metal that this is the metallic. But some are more extensive, and you always break some of that metallic bonding. So it's never totally decoupled, as you tell. So we take advantage of not being totally covered, where with 20-25 kilohertz of cycles, so per second alternative compression tension, we generate some plastic deformation. Plastic deformation means that you generate new chemically active surfaces. This process of plastic deformation generates heat, and you have then the heat, the compression force, and you are. I wonder if we start. Yes. One significant application now became a master process solution for joining of materials in cables, and the electrification of automotive industry relays in cables that have an extension of about 50 kilometers in our cars, okay, nowadays, 50 kilometers of cables, okay? And they are all welded, okay, and combined, and all the operation relays on this. Only the extremes that are mechanical, connected and disconnected are. So this is the sonotube that applies the vibration in some predefined direction. With this resin cycle, we generate the plastic deformation within the reactive surface, and with that plastic deformation, the heat and the pressure drive the matrix is made, and then the joint. So we have some atomic bonding and diffusion, as you can see, in between the elements of the plate. Also applied to polymers. Another important process is the explosion welding. Very specific domain of application, not exactly a welding process, is more a cladding process. One major domain of application is to bring together superstructures and sheets welded to decks that are of different materials. You want a deck, okay, that is resistant, double skin sometimes, made of steel, but anyway, you want a superstructure that sits on that lighter as possible so that you can maximize the load capacity for transportation of people and goods. Okay, so you produce the superstructure in aluminium typically, and the deck in steel. So how do you bring this together? By fusion welding is not possible. So you use a cladding of aluminium that is projected and generates good plastic deformation. So this was found in the Second World War by the plastic deformation of the projectiles over the skin of the vehicles, combat vehicles. That plastic deformation generates a chemically active surface, and the heat is such, you can see this wave shape, like almost the behavior of a liquid interface, because it's this third body domain that behaves as a liquid that is solid, okay, in temperature. And significant amount of diffusion in between the layers and high power. The joints produced by these solid state solutions are typically of the same level or even better than the basic. This is a big advantage also compared to fusion welding, where the heat affected zone or even the processing zone typically are problematic in terms of strain or impact. So, in this third body-based domain, we have the friction-based technology, large family. We will see friction riveting, we will see rotary friction welding, stitch welding, or pillar processing. We'll see friction surfacing, and some examples of friction welding, friction steel welding. In fact, friction surfacing coating technique was the origin of friction steel welding, a major step to apply this relatively difficult, low flexible solid state joints, because you have to have the matrix and the system dedicated for that material, for that shape. Okay, in fusion welding, non-conducting, you are very flexible on how to craft the joints. So friction steel welding brought that freedom that we can travel just like we travel with the fusion welding power source. There are a significant amount of variants, but even more important than friction steel welding nowadays are the innovations based on the concept, original concept. But it was doing tests of friction surfacing that friction steel welding in the States, that friction steel welding was invented by Ray Thomas in the welding institute. And friction extrusion is a good example of this creation of plastic, of non-chemically active surfaces with plastic deformation of ductile materials. Here, aluminium swarf that is brought together under pressure and heat generated by friction. Originally, the viscoplastic domain is produced, and then a new solid compound, fully sound, is able to be produced. Oops. I don't know why this did not start, but it starts now. So friction hydrophilic. In fact, if you understand this process, you understand a lot about solid state. Okay? It's a maintenance technique where if you find a defect inside of a structure, of a joint or something, you drill a hole and then you fill in with material that has similar or even better properties. All this in solid state, and this is now very, very important for the area of offshore structures okay? So you create a viscoplasticized layer. This is rotating, and that viscoplasticized layer is going to deform the base material and with new chemically active surface. And the heat, where is the heat generated? No. It is very obvious that our mind is separate. The friction is just generating a very small amount of initial energy that triggers we increase of temperature, brings down yield strength, and with the yield strength coming down, you start to have plastic deformation. And with plastic deformation, all the energy inside of steel, as an example, okay, being released by massive bulk dislocation system, the amount of energy is way higher than any other power source, and localized in the place where the plastic deformation generates the heat, and the heat enables the plastic deformation, and those enables the new chemically active surface and joint mechanisms to be activated. And the third body domain just grows to the top that you see. So the redness that you see is because steel in particular has radiation emission above 1000 degrees, so it turns red, okay, above it's not melting. Okay. So friction heating, this an outstanding invention also from some from a colleague of mine, so from Latin America, he's from Brazil, but he works in Germany. The internationalization is extremely important for gathering the best brains in these research units. They have impact. This is a good example of that. He is now inventor, he's now professor at Graz University in Austria. Okay? And he invented this friction for stud welding of metals to polymers. An outstanding difficult job, metal to polymer. So you see the deformation of the metal when it is inserted in the polymer. This is harder than the polymer, so it penetrates. Okay, but at some point, the deformation is localized in the metallic material. That string comes down and it starts to deform inside of the polymer, creating this clinching effect, mechanical joint. Okay. So why is it harder and then it gets softer? Yeah, try. You can speak in Spanish if you Spanish. Because you see the solution. You don't need to invent it, you just need to understand it. What do you understand? Everything looks obvious when you see it. Creating it is a different game. But even if you see it, now it's the National Geographic. You see the lion jumping on top of some other animal of the feeding cycle, okay, natural, and eating, and you think you understand. Okay? And people take lives to understand when it's hunting, what is hunting, what is the criteria, the social. So, but that's what I'm saying.
So there is a mechanical joint.
This is essentially clinching joint, generated but extremely strong. So there is no gaps in between the polymer and the metal. And the strength is extremely high. And this is being now explored for automotive industry, aeronautic industry.
But the polymer is a thermoplastic.
This is a thermoplastic in this situation. I'm not sure what was in this situation, but that is not in mind. but we are also testing it in heat. There was a PhD student that did his PhD at Aalto University, while the inventor was working in a research center in Germany. So the issue is the game of physical condition. The metal is hard, but has high thermal conductivity. The polymer is soft, but has low thermal conductivity. Okay? So you start to have heat dissipation in the interface between the materials. And the heat flows through the aluminum. As the heat flows, the strain comes down. But in the polymer that is very soft, because it has low heat conductivity, around the processed zone, the temperature is essentially room temperature. So if there is a moment where the strength of the polymer becomes higher than the strength of the zone that is being processed by the metal. So there is a gain. This is a multi-physical gain. Okay. And a change of complete paradigm of the formation part. Yeah, amazing to understand the mechanism. Rotary friction welding also has significant amount of applications to existing metal joints. Again, friction is the initial trigger for the temperature to go up and the strain to come down. As it comes, you apply the plastic deformation, that plastic deformation generates heat. And it generates the heat in the place that the plastic deformation is needed. Plastic deformation generates the heat, and both generates the new chemically active surface. Original surfaces come down, you have this new chemically active surface with heat and pressure, chemical and heat power with some time of forging. You then have the component, and then you just remove the flash. So this weld in a steel of 200-300 millimeters could take 8 hours to be done in fusion welding, in multi-pass fusion welding. Okay, so we can do it here in less than 1 minute. 8 hours, 1 minute. And the strength and the quality is strength and impact toughness properties are typically higher than modifications of inherent to processes of fusion. So application to different materials, stainless steel, titanium components, significant amount of application, or all our nowadays airbags are welded in solid state because you have polymers inside the bag and so on, so you cannot close the metal system in high temperature elements and so on. Although the localized temperature is high, but the amount of heat is low, so it would affect the internal part. You have also possible applications for titanium-based alloys in linear friction welding. The disadvantage is that you expose momentarily the plastic deformed part to the air, okay, until an airman flash forms and protects it, and it's possible to have sound part of the joint. This is friction surfacing, a coating technique. Oops. This is stainless steel, austenitic stainless steel applied over high strength steel, and this was a gift for a steel mill that is now named SSAB, but it was not a cookie that we provide to them in our research applications. We hope there is this multi-pass aluminum alloy deposition to create this filter system, so we create a height aluminum layer without having to remove material just by adding the material friction. And we can also produce with third-party components. We can also produce functionally equivalent materials, FGMs. And we have friction steel welding, where processed zone is encompassed by solid state cold material, an angle, and a shoulder, and then the probe brings doing the mixture and steering effect into the processed zone. So you will have a closed closed die system where the visual plastic material has to undergo significant amount of plastic deformation. So the shoulder prevents the material from coming out of the processed zone, and the probe has to be resistant and the tool is not constant. The processed zone, this can take any path, and brings the opportunity of joining materials. And aluminum alloys in general, they are thermomechanical processes. So this joint is exactly the same origin of the base material strength effect. You can see here applied in a polymer with some traces to understand the three-dimensional flow of the material as it gets away from processing. So the material flow provides the heat generation, and the plastic flow, and therefore the steering effect and the quality of the mixture depends a lot on the features of the tool. So the geometry and features that we provide to the shoulder and probe provides the properties for the processed zone. You can see the steered zone, very small grain, with a dynamic crystallization, and this is the original, similar to the original heat affected zone, but anyway, processed with much lower temperature than the heat affected zone from the fusion process. Different joints capacities, different materials, very easy for our nickel alloys, more expensive for nickel and titanium alloys because the tool is non-consumable and the price of the tool and material has to grow as we increase the temperature of the processing. And the temperature of processing is about from 70 to 80% of the melting temperature. We have solutions with static shoulders for complex shapes, and also we can have preheating and post-heating for thermoplastics. We have some innovations with Joule effect for processing the root so that we don't need to go so deep in the processing zone. And these are the tools, the most advanced tools nowadays for made of polycrystalline boron nitride tools for processing of steels, processing and welding steels, titanium, and steels. Techniques to avoid the exit hold. I will not take. I need to jump because the time is running fast. We have standards enabling us to address industrial applications. The first application, so this is a baby process in some way, it's from 95. Since then, we have a large evolution on the scope and domain of applications, mostly still oriented for aluminum alloys, a lot in shipbuilding of floors and several panels, where the price of an extrusion is proportional the gross exclusion is the width of the exclusion. And so what we do is that they exclude small components and then they weld them together with properties that are equal or overcoming the base structure. And then you have a payment at a lower cost. Applied in extruded also components to produce the tube of the shape of a train. Bombardier is one of the companies using these benefits for distinct quality products. So there is no welding in aeronautics. Everything is mechanically joined due to the sensitivity of materials and the alloys and titanium for the structure of critical components of the aeronautic transportation needs. And so this is being explored by several components to replace a significant amount of weight saving. Because everything that exists, if it's in mechanical joining, demands that you overlap the components. So you not only put third body materials to join, but you have also to use overlapping, which increases the weight of every joint. You have a window, okay, has about 7 components that are overlapped, okay, in that zone, just to build the structure and the relation from the internal skin, outer skin, and the structural resistance for the windows, as an example. And now you can produce it in butt joints. Okay, both Airbus and Boeing are exploring a very distinct domain of application is the new space launch system, okay? You know, from NASA, but also very known company now that is exploring this commercially. And so we produce the longitudinal wells and orbital wells in this structure, okay, which produces 61 meters tall joints for the liquid hydrogen and liquid oxygen tanks. Different thicknesses and different materials for optimization of automotive industry. Same here for some new rims, defense applications in defense for high alloy, aluminum alloy performance material. So it's absolutely critical that these vehicles are fast and so they are strong. So these demands materials that are very difficult to join and they really have high quality. Otherwise, lives are depending on that for the movement. Applications in artistic components, so Nobel Peace Center in Oslo influences homemade in aluminum efficiency welded and required by the architect. Very important field. Do we have in Colombia nuclear power plants?
No.
Okay.
No.
Or for the good and bad, so Finland would never be able to support the level of industrialization and live with very harsh winters, long and low temperature winters, without a local production of energy. Same for Germany, same for France. So all industrialized countries, they cannot rely on solar and wind energy. They play a role in the mix, but the most efficient and safe anywhere nowadays are most solution. So it is nuclear power plants. This nuclear residual material waste needs to be taken care of. Okay, and there is many tons now of the residual pellets that have no more useful, that are no more useful for producing energy, power density that we need, and we need to store them. And so we are putting them now in cast iron research to detain the energy. The radioactive energy and temperature of these pellets, and then we have copper canisters to protect them from corrosion. And these are designed to survive the utmost conditions of earth can provide us in earthquakes and to the extreme of life existence. Okay? So they are forever. We are producing these, and the weld of the canisters now are very critical because no man can be there. It has to be automatized systems, and so we are welding the copper cover to the canister cylinder. This is a copper cover. That's why we weld. This is 30 millimeters thick weld. Okay? In one pass, totally automatized and easy to inspect in quality with the ultrasonic non-destructive text. This is an application in steel. I'm not sure that you are aware. How much are you aware about the war that is going on in Europe right now? But Russia and Europe are connected by these tubes and pipelines for gas mostly now, and the new pipeline that existed, it's just ready to be used. It's really sure that it's actually going to be used under the actual political conditions. But anyway, this will explore the efficiency welding for welding in the local or even inside. Okay, with the automatized system, it runs over the star, comes out in a runoff pair that you can machine out. Okay. You can see the temperature. Oops. So I will leave a comment on this for time. Another very interesting application is are not anymore produced, or if they are not massive, they have everything portable shapes, not fixed. Desktops and laptops. But all these
sensitive electronic components of Apple IMAX were closed at the end, and they were never intended to be opened by friction stimulation. Okay? Very sensitive components that are protected by the low level of energy. So we apply it also in healing of casting for better distribution of properties in casting components, metal matrix composites. We can also reach with fine grain superplasticity behavior local, and this is the friction stir processing is not working. So another evolution from friction stir welding that provides a different result is friction chaining. We are able to produce closed in subsurface channels that can take any pass, okay, in the material. So think how you can produce a channel inside in one action, closed channel in one action that can take any pass. You can drill, okay. You could even produce it under some circumstances with casting, but you cannot be very complex, otherwise you cannot extract the shape from the inside. So now we are producing these channels that can take any pass. This is for conformal cooling, so dedicated pass that goes exactly to the most preferential heat transfer locations. This is an important solution. Because of the viscoplastic domain, the material that is being processed takes the shape of the anvil of the tool, so we can have micro forming. We can also have this self-embossing forming. This is friction spot welding. So instead of doing it in fusion welding, we can do it in solid state. Welding aluminum with resistance welding is extremely difficult because it relies on the resistance to generate the heat. But if the resistance is low, electrical resistance, and thermal conductivity is high, doing it with fusion is extremely complex. And so we have now this very interesting approach. I don't know if you have seen, but so we have flow of material with 3 rings. Comes after this or not. So we have 3 rings. This black goes down, the blue goes up, okay, and we promote the steering of the materials with the same volume and forging of the processor. And this takes about half second. So very high competitive process. Additive manufacturing concepts for near-net shaped manufacturing. And we come now to the last item in our agenda, okay? And I'm sorry, so for the extra time that I've taken from you. So one distinctive evolution that we promoted at our research unit was taking advantage of that flash that you saw in friction surfaces. And now we are using the flash to produce tubular shapes without any weld. And so we produce tubular shapes without any matrix and without any weld. Tubular shapes are produced by this complex welding process of informing and welding, okay? Or then they have to be extruded, and in steel, they are for large cross sections. They are extremely difficult to produce. And so the amount of tubular system, and they are producing big amount of tons, are the minimum amounts economically viable to be produced. We can produce it in several materials, in stainless steel, aluminum, titanium, as you see here. We can produce it with uniform thickness, different thicknesses, varying the shape. I wonder if this runs. This is a tentative spin-off, so we have a company, this Altu company. It's in the early stages of evolution.
So you can see the concept of manufacturing based on the flash with no dies. We produce a cylindrical shape and we can change the thickness and the shape according to the plunging conditions, and it's very significant impact in applications existing, waiting for small tubes in specific materials that don't exist in the market. Another example is the evolution of friction chaining that we saw. So now we produce channels, but we also are able to weld different materials in the same operation. So we produce a channel in a bulk material and then a weld. With these, we combine the properties, and we can use copper that is expensive and heavy in a very thin sheet to do the thermal management of the system. And all the mechanical systems, essentially, or electronic systems, require thermal management. Otherwise, all the energetic phenomena are dissipative, and temperature jeopardizes the operation. So thermal management is critical for everything. Okay? Everything that we do, even for us, okay? You run, you sweat, you have your thermal management immediately. Otherwise, you die. Okay? And you cannot live very hard. And all the materials of this mechanical system have that. So we use the copper here to do the thermal management, and then we use the low cost and light material to do the thermal management of the copper. Okay? And we have no interfaces. This is now being explored for several applications in aeronautics for electrical motors. So we can go inside with the copper, doing the thermal management, and then use the aluminium, okay, to do the thermal management of the copper. And the copper then is explored to do the thermal management of the stator, as an example. Or also for batteries, okay? So again, we have aluminum. This is for electrical aeronautics and battery systems that needs to be thermal managed and very light. And we are using air with the natural convection to do the thermal management. So our aluminum system is producing the management of all the battery surface in one action. So we have the skin, we have the thermal management unit, and by hybrid chaining, we are now able to produce positioning and thermal management decomposed. And then the new big step in our innovations is joining metal to polymer, okay, in linear joints, and we are quite unique in that way in the world. So we produce linear joints, okay, with between aluminium and structural thermal polymer, which is big here, or polyether ketone, by a mixture of clinching and some small scale diffusion. And this is the joint. These are tests of the joint that are fracturing always in the weakest material, so taking the strain of the weakest material, quite high performance. How does it work? So what you see here is that we deform the aluminium, okay, and the polymer goes inside with the similar volume of the aluminium goes inside the polymer goes inside the aluminium, okay, and we have the clinching mechanical interlocking effect, okay. At high temperature, we have also some adhesive and some small diffusion. So extremely strong joints. But the temperature for material flow of aluminum is about 400 degrees. Okay? The aluminum behaves like this. We are able to deform it and close the surface in three-dimensional flow, okay, at 350, 400 degrees. And this melts at 120, and at 180 is vaporized. So how can we produce this? Okay. So we use these extrusion matrix. They are made of titanium that has very low thermal conductivity, so they protect the energy, the thermal energy that we transfer from the aluminum into the polymer. And they are harder than the aluminum, so they are used as extrusion. So we extrude aluminum into the polymer and protecting the polymer from the energy necessary to extrude. This is the, and then we take this in energy to produce now joints over joints. And new airplanes can now be produced with polymer as they are joint, which is no certain bottom. And the application for this is now being explored in fuel cells. Okay, that is a multiple engineering material joint, multi-made in terms of requirements of operation, and we have a brilliant solution to produce small cells that enable high pressure and therefore very high power density, electrical power density from the fuel cells. And this is it. And I'm so